Welcome to Astronomy 102, Stellar Astronomy. This is TJ Lipinski. Alright, so this is Chapter 1. We're going to go over this. This will actually take several videos. The recorder that I'm using will only allow me to do this like 15 minutes at a time, so you've got to break these up. Anyhow. So this is the textbook, of course, which you get when you go onto Blackboard and you log on to the Pearson website. It says e-text. That's the one that we're using. All right. Anyhow, so Chapter 1 is about you can kind of think of it as what ancient peoples could see and tell from the night sky without the use of any kind of equipment like telescopes, of course, which came into play about 400 years ago. But this is all before that. All right, so this is the kind of thing that happened before what we would consider modern astronomy. So this is basically like ancient astronomy. These are the different subjects that we're going to talk about. Where we are in the universe. Our local system, and talk about the galaxy and other galaxies and things like that. We'll also go over the scientific method, as you always do with all science courses. It's a very important thing to understand the scientific method. It's absolutely crucial. It's important to understand how it's different than other forms of human activity. So we'll look at the night sky, we'll look at the motion of the Earth, we'll talk briefly about angular measurements, which like degrees, minutes of arc, seconds of arc, or what are called arc seconds or seconds of arc. And then we'll do the motion of the moon, measuring distances, and then we'll use this method that has been used since ancient times, called parallax. All right, so the Earth. The one thing that we have to understand. Ancient peoples always they thought that the Earth didn't move because it doesn't feel like it's moving. And that's that's kind of a natural way of if nobody ever told you that the Earth was going around the sun, and you just grew up and watched the night sky, watched the sun go across the sky, from east to west each day. It would seem like the Earth wasn't moving, but of course, nowadays we know it's moving. Even in ancient, 2,000 years ago or more, there were some people who suspected that the Earth moved. Briefly, let's go into what the universe is. That's a big subject, obviously. But it's really everything. It's space. The distance between 2 points is kind of a good way of defining space. Although it's a little more involved than that. And time, of course. Time is a dimension, very much like space is dimension. And then, of course, matter and energy. So these are all the things that we know of that the universe consists of. Okay. So astronomy, we really study the entire universe. We study the very large, and of course we study the very small. So it's actually really important to understand the powers of 10 and using scientific notation, 3 times 10 to the 8th power. And also understand what the units are, and do a little bit of conversion between, for example, between light years and meters, or light years and kilometers, things like that. All right, I'll do that separately. Right now, I'm just going to do this PowerPoint presentation. So when you go out into when we start expanding our knowledge of the universe. We know that we, of course, live on the third planet from the sun, and our sun is just one of perhaps 200 billion stars that make up our galaxy. The reason I say perhaps is because we don't know exactly how many stars there are in our galaxy. We can't actually see our entire galaxy because we're a part of it. So what we do is we look at other galaxies and we look at the mass of our galaxy and compare it to the mass of other galaxies, and then we make a good scientific estimate about what the number of stars in our galaxy is. And of course, we can't in astronomy. The space is the amount of distance that you're talking about is so vast that it really starts to lose any meaning to start talking about things in centimeters or in meters or even kilometers. You really need what are called light years. So for example, if you stay within the solar system, within our solar system, we use a special unit, the distance between the average distance between the Earth and the Sun, and that's called 1 astronomical unit. So if we're within the solar system, that's a perfectly good unit of distance. When you get outside the solar system, the stars are spaced very, very far apart. And so what we do is we use the distance that light travels in a year. Light has a constant speed. It travels at 3 times 10 to the 8th meters per second, and it always does that, no matter what the motion of the object is or the observer. That was actually a great discovery that Einstein made a long time ago, over 100 years ago. Anyhow, so we use this thing called a light year, which sounds like that it's time. It is actually both time and distance. Although it's technically used as a distance measurement, but you can think of it as a time measurement as well. If you see an object, for example, that is, I'll just use this example, 100,000 light years across, or 100,000 light years away, then that light took 100,000 years to travel that distance. Then you also know that you're looking at the object as it was 100,000 years ago. So when you look out into space, especially into deep space, you're always looking back in time, and that even works. That even counts towards within our solar system. When we look at objects in the solar system, they're maybe a few light minutes away or light hours away. So that's like the outer planets, for example. But the nearest star to the sun within our galaxy, right, one of the other of roughly 200 billion stars within our galaxy, the Milky Way, the nearest one to us, and by the way, we're nowhere near the center. We're way out here. That's a different topic. We'll get to that much later. But the nearest star to the sun is about a little more than 4 light years away. And that's the closest one, right? So all the stars within our galaxy are in a distance roughly 100,000 light years across. We'll talk about the thickness of the galaxy and things like that later. The spiral arms, the fact that we have a spiral galaxy, that we live in a spiral galaxy. Not all galaxies are spiral, by the way. But again, that's more for the rest of the semester, really, for Astronomy 102. Let's talk briefly about the scientific method, and this is really important. Here's what I always mention. If you look, for example, at a beautiful painting, the Mona Lisa, for example, most people would agree the Mona Lisa is just this masterpiece of art. But the thing is, art is different from science in the following way. Of course, you could take do a survey and, kind of make it sound scientific that, the Mona Lisa is the most beautiful painting ever. But it would just be a survey of human beings, and then, are you talking about just the human beings that are currently alive? What about people who saw the Mona Lisa in the past, and so forth? But the point is, saying the Mona Lisa is a beautiful painting is not a scientific theory, right? It's not testable. Even if you're taking, surveys of human beings ever since the Mona Lisa was painted, it still would not be considered as scientifically testable. You have to be able to perform what's called an experiment, of course. And in fact, that's why we have, a laboratory portion of science classes, because the scientific method absolutely requires us to be able to test ideas. It's wonderful to come up with ideas, and there are people who are really good at coming up with ideas, but what makes it scientific, what happened about 400 years ago, really, there was some science, of course, before 400 years ago, but what we would consider modern science, the idea that you have to perform experiments, really established itself roughly 400 years ago, right after the Renaissance, or towards the end of the Renaissance. Anyhow, again, it's absolutely essential. This stuff here that things should be simple and elegant. That would be nice if that was true. Let me mention this. Philosophically, scientific theories can be proven wrong, but never 100% right. Because, of course, you can always perform another experiment where the idea turns out to be wrong. Although it's not quite as simple as that. It's usually some small aspect of the theory. There's some new experimental evidence that shows that there's some aspect of the theory that is incorrect. And so modern science is we still try to come up with big ideas, absolutely, but usually scientists are in the business of exploring small aspects of big ideas and showing, through experimentation, whether they're right or not, and then trying to come up with a better idea, and of course. It's always in the physical sciences. It's very important that we can actually look at mathematical relationships between different quantities, and then we can adjust our theories to see if when we have more evidence, and then find different mathematical equations that describe what's going on. Right, so this is this famous circle. So basically you have observation, and then you look at something in nature. You come up with a theory, which is just an idea that tries to, if this, when you look at something and you come up with an idea that explains it, the theory should come up with some predictions. And see, of course, the modern part, the thing that happened, this observation and coming up with ideas or theories, that's thousands and thousands of years old. But the idea of coming up with predictions from, that can be shown, that the predictions, of course, you're talking about experiments, that happened roughly 400 years ago. And again, it's a never-ending cycle, but really the theories, what we end up doing, as I mentioned earlier, is we look at little portions or little aspects of the theory nowadays, and we try to prove the little aspect of it, whether right or wrong. All right, now it looks like I'm about to run out of time. Let's see. So this is when you look out at the night sky. At any one time, depending on which hemisphere, if you're in the northern hemisphere or the southern hemisphere, you can see roughly 3,000 stars that are visible to the naked eye. Of course, there are a lot more stars